All right, welcome to a short conversation about lemniscates. We are looking at various r and theta equations and graphing on the polar coordinate plane. And this very unusual equation does have an r on the left-hand side, as did all of our previous equations in this section. However, this one says r squared, which when it comes to graphing this equation becomes a little bit challenging. If you were going to graph this, and I'm actually speaking out of turn because I didn't test this myself, but if I took the square root of both sides of this equation, my guess is that I would need to put a plus or minus on the right-hand side of the equation. Plus or minus square root of 9 sine 2 theta, which would of course become plus or minus 3 times the square root of sine 2 theta. That would be a good experiment for you to do if you have a graphing calculator or you want to go into Desmos and plug in both sides of, as a matter of fact, I did that already. And it worked. I just took the square root of the entire right-hand side. You can see it there toward the bottom right corner of the screen. I typed that in yesterday, and so I forgot I had just typed it in without a plus or minus, or without having to type it in the equation twice and negating one of them. And it did indeed give me the entire graph, which you're seeing in the top right corner of the screen. So good to know what the target is supposed to look like. And I will tell you also that the length of those petals is equal to the square root of 9. 9 as well, I don't want to, I'm just spoiling the whole thing, right? We've already talked, you already know what the graph looks like. What I wanted to do with you even before that was to give you the values that are in this table. I plugged in the theta values, calculated the r values. We can plot some points aiming in the direction of 0. We're going to move 0. Aiming at pi over 6, we'll go out almost 3 units. At pi over 4, we will go out 3 units. At pi over 3, we'll come back into that 2.79 number. And you can see that that causes us to draw just this one petal. You are welcome to see what happens if you then continue plugging in theta values and plotting points. The next one you could plug in would be, I suppose, pi over 2. My guess is that's, pi over 2 is actually in the table and gives you a 0. But if you then plugged in 2 pi over 3, it would be interesting to see what happens. Will you get 0? Will you get undefined? Are you going to get something with a negative r value that pushes you into the 4th quadrant? Probably not, considering that if you look in the top right corner of the screen, this graph lives in the 1st and the 3rd quadrants. So it'd be interesting if you wanted to try that out and see what happens if you continue plugging in theta values. The other option, instead of doing that, and this might be a specific component of a test question that you could see, would be to demonstrate the 3 symmetry tests and then use the results of those 3 tests to help you determine what, if any, additional parts of the graph should be drawn. And if you go through and do those 3 tests, which of course I recommend that you do, my guess is, now I've done this problem, but I haven't done it like in the last 6 months, so I don't actually remember what the results of the tests are. But if I had to guess, based on the graph that I'm seeing in the top right corner of the screen right now, my guess is that the test for pole symmetry is going to pass, which means that the graph is definitely, necessarily going to exhibit pole symmetry. And pole symmetry is tested for by plugging negative r in for r, and then trying to manipulate the equation so that it looks exactly like the original. If you want to look at this one together, right at the top of the screen is the equation, and if you plug in a negative r for that r value, what is negative r, in parentheses, squared? I suppose I could even write this down. What is negative r squared? If you said r squared, you're correct. And just by that one simple motion, we have arrived at an equation that is identical to the original equation, which means that this test for pole symmetry means that our equation passed the pole symmetry test. Which means that our graph will definitely exhibit that type of symmetry. So we can take the point that was in the direction of pi over 6, reflect it over the pole, which would give us a point here. I like to draw my reflected points as little open circles so that I know that they came from reflection. The pi over 4 flops over the pole, and pi over 3, that point, reflects over the pole, giving us these other 3 points. Did I draw those out far enough? I didn't. I drew them at a length of 2 instead of at a length of 3. Sorry. Those should have been here and here and here. And then if you wanted to draw it dashed, you could. If that's going to be confusing to you later, then just draw it as a solid curve. And that is the other half of your graph. Nice. I recommend that you attempt this process. You could just shortcut it and take the square root of both sides of this equation and plug it into a graphing calculator or into Desmos and see what the resulting graph is going to look like and how long the sort of length of each petal is, how many petals there are, how it's oriented. Or you could take some theta values and plug them in and calculate corresponding r values and do a little heavy lifting just this once to make sure especially that you have a little experience with the rhythm of solving this on your own, just in case you're not allowed to use a graphing calculator on the test that is on this material. My students will not be using a graphing calculator when I test them on this material, so they should definitely make sure they know how to plug this information into their scientific calculator. The good news is, well, there's so much good news. One is that we're going to talk about parabolas next. Very exciting. The other good news is that we're going to pop down to the Lemniscates section of the summary page, and you're going to get an insight as to what this graph should look like. So the end of our conversation about Lemniscates is going to happen right here. And notice that the loop length is, as I mentioned earlier, determined by, it was determined by the 9. However, the length of those loops was not actually 9, it was 3, because the coefficient on sine and cosine, it looked like a 9, but that 9 was actually a 3 squared. So the loop length is determined by A, which you might want to write in as being the sort of square root of the coefficient on the trig function. And then there's no question about number of petals like there was with the rose curve. There's always only going to be 2 petals. However, when you're working with the sine function, you will have symmetry with respect to the pole, as we saw in the example and as still appears in the top right corner of the screen. Interesting is going to be, and I hope you'll discover this on your own, that when you're using the cosine function to graph a lemniscate, you end up having symmetry with respect to the polar axis, which is the same as the x-axis. Otherwise, other than those 2 orientations, the only thing that you can do is change the loop length by increasing that coefficient in front of sine or cosine. Make sure that you are, please, keeping up with where these pieces of information are located on your formula sheet. Make sure that you're using them when you're completing your homework assignments, if you're one of my students, and continue paying attention to the patterns that are present as you go through and draw these graphs. I mean, most of the patterns are summarized here on the summary page. Don't just sort of march through it blindly and kind of mechanically in order to complete the homework assignment. Also try to internalize it a little bit and be aware of the patterns. That's going to help you be able to complete your test questions more quickly and more accurately, which typically results in a better grade. So a good use of your time, hopefully. That is it for me, and there's another link right below me here. So wait, I almost forgot that I wanted to look at the graph of a sideways facing parabola with you. It's only this one question, so do please make sure that you click on this link below so we can take a look at that graph, talk about one little characteristic of it, and then we will be done with this section. See you there.